Hi, students. Professor Gray here. We're going to talk about Lewis structures right now. And we've talked about how to do Lewis structures with single atoms, but now we're going to talk about how to draw molecular structures using the Lewis dot structure rules. Now, I have already started number 1 because I tried to do this video a couple times before, and I had to mess with my settings a little bit, so that's why there's some writing there already. But anyways, number 1 says count the total number of valence electrons in the molecule. And our example is PCl3, which is phosphorus trichloride. So in order to add up the total number of valence electrons in the entire molecule, we need to add up the valence electrons for each atom. Now for phosphorus, what we'll do is we'll take a look at the periodic table and we'll see that phosphorus is in group 15 or 5A, which means we're going to have 5 valence electrons for phosphorus. Now for chlorine, what we have is we have group 17 or 7A for chlorine. So that means that each of our chlorines is going to have how many valence electrons? 7, that's right. So 7 for each one of those. So 7 plus 7 plus 7 is 21, plus 5 is 26. So we have 26 valence electrons available for drawing the structure. So number 2 says use atomic symbols to draw a proposed structure with shared pairs of electrons. And the bullet point there says atoms don't tend to bond to other atoms of the same element when they can avoid it, which means that a chlorine won't bond to another chlorine if it can bond to an atom of a different element. So what we're going to do with PCl3 is say, okay, if the chlorines don't like to bond to each other, then they must be putting phosphorus in the center. And another way to think about it is that the atom that occurs least often is often the one that's in the center. Not always, but it does that a lot. So we're going to use atomic symbols like rule number 2 says, and we're going to propose a structure. So I drew a chlorine to the left and the right and on the bottom. You guys could draw it to the left and the right and the top, or to the top and the bottom and the left, or the top and the bottom and the right, however you guys want. It's going to end up being the same structure, and we have to remember that our molecules will tumble around in our beaker, so if we get the right structure drawn, we've got the right structure drawn. So number 2 also says at the bottom that carbon is the exception to the general rule that atoms don't tend to bond to other atoms of the same element if they can avoid it. And that's because carbons love to bond to other carbons. And they also love to bond to hydrogens. But if we remember carbons like to bond to other carbons, then we'll have a lot easier time when we go on to draw big old molecules called hydrocarbons. All right, going on to the next slide. Number 3 says place lone pair electrons around each, and that should say atom, except hydrogen, to satisfy the octet rule beginning with the terminal atoms. Now remember, the octet rule says that all of our atoms want to have 8 valence electrons, except for hydrogen and helium. Those two want to have a duet, which means they want 2. So from the previous slide, we have 26 valence electrons available for our structure. And our basic structure that we drew was this. And we want to remember that each of those single bonds between the chlorine and the phosphorus are 2 electrons. Those are 2 bonding electrons. Now number 3 says place lone pair electrons. And remember, lone pair electrons are non-bonding electrons around each atom except hydrogen to satisfy the octet rule. So we've used up 2, 4, 6. Those are from those single bonds right there. So we have 2, 4, 6, 8, 10, 12, and we want to distribute them evenly because nature loves symmetry. 14, 16, 18, 20, 22, 24. So we've used up 24 of those 26 available valence electrons. And we can see right now that each of our chlorine has one bonding pair. That's the single bond right there. And they have 3 lone pairs. And that means that each of our chlorines can pretend that it has 8 electrons around it, and that gives it an octet, and that makes it happy. So all of those chlorines are happy. But what we'll notice about the phosphorus in the middle is that it doesn't have an octet. It has a sextet, because each of those single bonds is 2 electrons. So we have 2, 4, 6. And the rule is that we have to satisfy the octet. Now, luckily, we've only used up 24 of our electrons in the current structure that we have, which leaves 2 extra. And rule number 4 says place any leftover electrons on the central atom. Well, we have 2 leftover ones, so we're going to go ahead and put a lone pair of electrons on phosphorus right there. And now phosphorus can pretend that it's got 8 electrons around it and that it has an octet. So we've satisfied the 2 main rules, which is that everybody has to have an octet, and we have to use up exactly those 26 valence electrons that we have available for this structure. And that brings us to number 5, which says if the number of electrons around the central atom is less than 8, we have to change single bonds to the central atom to multiple bonds. So multiple bonds are double or triple bonds. And what on earth did I just say other than a whole lot of blah, blah, blah? Well, let's go ahead and go through the process. So we can list our atoms and our valence electrons. So we have carbon, hydrogen, hydrogen, and oxygen. And if we look at the periodic table, we'll see that carbon is in group number 14, or 4A, which means that it has 4 valence electrons, and you can see the 14 or the 4A up there. So it has 4 valence electrons. And by the way, this right here is a big V for valence, and then a little E and a minus symbol for electrons, and then an apostrophe S for valence electrons. Hydrogens. Hydrogens are in group number 1, or 1A, which means they have how many valence electrons? 1, that's right. So 1 for that hydrogen and 1 for that hydrogen. And then oxygen. Oxygen is right here. It's in group number 16, or 6A, which means it has how many valence electrons? 6, that's right. Okay, so we have 12 valence electrons to work with for this structure. So what we know is that carbons like to bond to hydrogens, and we also know that atoms of the same element don't like to bond to each other. So if we're starting a structure, we might put hydrogen on either side of this carbon here, because carbons and hydrogens like to bond to each other. Also, because you have to try something. So you have to draw something. And don't worry right now about whether you get it wrong or right, because you're learning. So what we also are going to do is we're going to bond oxygen to this carbon. And again, don't worry about whether it's wrong at this point. We can always erase. So we've used up 2, 4, 6 of our valence electrons out of our 12. And that means that we have 6 left over. So what we want to do is we want to follow the rules. And the rules say that we're going to distribute the leftover electrons to our terminal atoms except when they're hydrogen, because hydrogens only like to have a duet. So they're not going to have a lone pair on them. Don't ever, 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 ever put a lone pair on hydrogen until you get advanced in chemistry and you're going to work with something called a hydride, which has a lone pair and a -1 charge, but we're not going to do that in here. So don't put lone pairs on hydrogens, okay? They're happy with a duet. That leaves us with oxygen, because oxygen's our other terminal atom, which means it's on the end, like a terminal disease, you're at the end. And if we have 6 left, that means that we say 2, 4, 6. So that means that each of our hydrogens has a duet, and our oxygen has an octet, 2, 4, 6, and 8. But there's something wrong with this structure. It's the carbon in the center. The carbon only has a sextet. So if we look right here, we can see we've got 2, 4, 6. And the rules are we have to use up 12 valence electrons, and we have to give everybody an octet, or in the case of hydrogen, a duet. So we have to fix something here. And what we need to do is we need to change the single bond between oxygen and carbon into a multiple bond like the rules say. Let me get this structure a little bit cleaned up here. Okay, so let's go back to this structure right here. And carbon says to oxygen, hey, the rules are that we both have to have an octet. You have an octet and I have a sextet, and that's not fair. It doesn't follow the rules. So I want you to share some of those non-bonding electrons. And oxygen's like, I don't know about that, but okay. It'll take some of its electrons and it flips it down here to make the second half of a double bond. And what we can draw now is this structure right here. So we have a double bond to the oxygen, and I'm going to move the lone pair electrons that are on the top here to the side here. It doesn't really matter if you draw them top and left and top and right or left and right, but convention is that we draw them left and right when there's 2 pairs. Now what we can see is that we've used up our 12 valence electrons. So we've got 2, 4, 6, 8, 10, and 12. And we can also see that everybody has a duet or an octet. So the hydrogen right here can pretend that it's got a duet. The hydrogen right there can pretend that it's got a duet. And the carbon right here can pretend that all 8 of those electrons belong to it. So it can pretend it's got an octet and makes it happy. And the oxygen right there can do the same. It can pretend it's got an octet, or it has all those 8 electrons to itself, because carbon and oxygen are sharing. So it makes everybody happy. Okay, now what happens if you draw the wrong structure? How will you know? Well, you'll know that you'll have the wrong structure because either you won't have used up the exact number of valence electrons that you counted up in the first place, or everybody won't have an octet or a duet, and there'll be some kind of unhappiness in your molecule, and that should set off an alarm to you that your structure is wrong. So again, you have to make sure that you've used up the right number of valence electrons and that everybody has an octet or duet. All right, moving on to some problems. So let's draw the Lewis dot structure for Cl2O. So just going through the regular process, we will list our atoms and the number of valence electrons each atom has. So using the periodic table, we can see that chlorine has 7 valence electrons because it's in group 7A or 17. Also, chlorine is a halogen. This column right here, those are our halogens, and they're always going to have 7 valence electrons. So that's one of those ones you should probably get really familiar with because it'll help you do things quicker and it'll make things easier on you. So chlorine, each of those is going to provide 7 valence electrons for this structure. And oxygen is right here, and that brings along with it 6 valence electrons because it's in group 6A or group 16. So we have 7 plus 7, which is 14, plus 6, which is 20. So we have 20 valence electrons available. Now, one of the hints was that atoms of the same element don't like to bond to each other if they don't have to. And the other way we could say that is that the atom that occurs least often is often the one that's in the center. So let's go ahead and stick oxygen in the middle and bond chlorine to each side of it. And let's go with that and see what we come up with, if that's the right structure or not. Now, how many valence electrons have we used up? 2, 4. Because remember, for each of those single bonds, you've got 2 electrons there. So you have 2 bonding electrons. So 20 minus 4 is 16. We've got 16 left over to use. So 2 and 4 from the bonding electrons, 6, 8, 10, 12, 14, 16. So now we've used up 16, so we've got 4 left over. So if we put those 4 there and there, and we said, okay, we've used all 20 valence electrons, and we left the structure like that, it would be wrong. And the reason is because we're not following the octet rule. Now, if we count around chlorine, we can see that we have 2, 4, 6, 8, 10. And 10 is more than 8, so we're not following the octet rule. And remember, the shared electrons, chlorine is pretending that those are its own, so you can count up 10 right there. So ding, ding, ding right there, wrong structure. So let's go back and take those bonds away from between oxygen and chlorine and go back to this structure right here and see if we can fix this. Okay, so each of our chlorines has 8 valence electrons around it. So 2, 4, 6, and then 8. So you can see that right here. So both of our chlorines are happy. So we're not going to want to give chlorines any more lone pair electrons, and we're not going to want to double bond it or triple bond it. And we have oxygen that has a duet right now. So right now it's just got those two single bonds on either side of it. And it's like, okay, well, I have 2, 4. So sorry, I said it has a duet. I meant a quartet. So it has a quartet and it needs 4 more to make an octet. And we have 4 valence electrons available. And if we go back to this slide right here, we could see that we had almost the same exact situation with phosphorus in the middle when we went on to the next slide. And what we did was we followed rule 3 that said place a lone pair electrons around each terminal atom. And then if you haven't done this, then, if you haven't satisfied the central atom, then go ahead and put those leftover electrons on the central atom. So let's put the 4 leftover electrons on oxygen right there, and then we can see the oxygen has 2, 4, 6, 8, so it's got its octet. So we've used up our 20 valence electrons, and everybody has their octet, so we've got a winner here. All right, so C2H4. Let's go ahead and add up our valence electrons for C2H4. So we've got a couple of carbons and we have 4 hydrogens. Each carbon has 4 valence electrons, and we've got 2 of those, so 2 times 4 is 8. And each hydrogen has 1 valence electron because it's in group 1 or 1A, and we've got 4 of them, so that gives us 4 electrons from those 4 hydrogens, and that's 12 electrons total. So we have 12 valence electrons to work with here. Now we have to just write some kind of structure, and we have to remember that we don't want to have hydrogen being bonded to more than one other thing. It just wants a single bond and that's it. No lone pairs, no double bonds, no triple bonds. So that means that it's probably going to be a couple of carbons that bond to each other, which is good because carbons like to bond to each other. So we'll bond a couple carbons to each other and go, yay, they're happy. And then we'll distribute the 4 hydrogens equally around the outside. Now you guys can draw them top and bottom, or you can draw them top and to the right, or on the left carbon, top and to the left, or to the left and to the bottom, or any way you want, as long as you've got 2 hydrogens on each of those carbons, because again, nature tends to be symmetrical. Okay, so 12 valence electrons available, and we've used up 2, 4, 6, 8, 10. Now the rules said after this, what we're going to do is distribute any leftover electrons, which we have 2 of, to the terminal atoms unless they are who? Hydrogen, that's right. And all we have for terminal atoms is hydrogen, so we can't distribute those 2 leftover electrons to the hydrogens here. We're going to have to use the next rule, which says go ahead and put them on the central atom. Well, there are 2 central atoms here, both of those carbons, so we pick one. If we pick the one on the left, then that carbon now has an octet. So you can see 2, 4, 6, 8. It's got 8 of those electrons around it. It's got 3 bonding pairs, and it's got 1 non-bonding pair, which we also call a lone pair. So this is its octet right there. Now, there is a problem here, and I'm wondering if you can see it without me telling you what the problem is here. Besides my erasing skills. My erasing skills are terrible. Okay, so let me draw this back in here. Okay, so the carbon on the left-hand side has an octet, all of the hydrogens have a duet, and the carbon on the right, is it happy? No, it only has a sextet. So you can see it has 2, 4, 6. So the carbon on the right says to the carbon on the left, hey, I only have a sextet and the rules say that I have to have an octet, so you need to do what with the lone pair electrons over there? You need to share. And the carbon on the left is like, all right, I don't like lone pairs anyways, so I'll throw those lone pair electrons in between us right there and turn them from non-bonding electrons into bonding electrons. And what we get is a double bond here, which is 2 bonding pairs or 4 bonding electrons. And each of our carbons has 2 hydrogens on them. And I'm going to draw them out at angles like this because I can, and that's okay too. So now what we can see here is all of our hydrogens have a duet, which makes them happy. And our carbons, they can both pretend through all of this sharing that they have octets. So you can see that right here. 2, 4, 6, 8. Okay, for each of them. And then if we wanted to count up just to make sure that we definitely had 12 valence electrons that we used, we could go, okay, 2, 4, 6, 8, 10, 12. Ding, 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 ding. We've used up 12 valence electrons, and we have everybody with an octet or a duet here. So just to draw this structure again for you guys, you can draw the hydrogens out to an angle or up and down like this. But just because there was colors every which way on that one, I wanted to draw it again for you guys. Okay, so number 3, we've got C2H6O. So for this one, we're going to follow the rules again, and we're going to say, okay, which atom do we have, and how many valence electrons do we have? So we have 2 carbons, we have 6 hydrogens, and we have 1 oxygen. Each of our carbons has 4 valence electrons, and we've got 2 of them, so that's 8. Each hydrogen brings with it how many valence electrons? 1, that's right, and we've got 6 of them there, so that's 6 total. And then oxygen is in group 16 or 6A, so a single oxygen brings with it 6 electrons. So we have 6 plus 6, which is 12, plus 8, which is 20. So we have 20 valence electrons to work with to make our structure here. Okay, so we know that carbons like to bond to each other, so let's just go ahead and draw carbons bonding to each other. And we can see that we've got 6 hydrogens to distribute. So if we just went ahead and distributed all of our hydrogens around all the edges there, we'd go, we forgot to put oxygen somewhere. So we've got to put oxygen somewhere, and that's okay that we made a mistake because we're learning. So we go ahead and we just erase one of these on the end and try something else. So we go ahead and we put oxygen right there, but then we go, oh, well, I still got to put one of the hydrogens somewhere. So let me try putting it over here. And then we got to say, well, okay, how many valence electrons have I used up so far? Because I've only got 20 of them. So go ahead and count. We've got 2, 4, 6, 8, 10, 12, 14, 16. So we've used up 16 and we have 20, so that means there's 4 left over. And that's actually pretty lucky, because if we look at all of the carbons and hydrogens in this structure, we can see that all of our carbons and hydrogens are actually happy. They all have an octet or a duet. So all of our hydrogens have their duet. They're sharing those 2 electrons, so they're pretending they have their duet. And all of our carbons, oops, that goes down there, have 2, 4, 6, 8 around them and 2, 4, 6, 8 around it. But what we can see is that that oxygen isn't happy. It has a quartet, and it needs 4 more electrons around it to make that octet. So we can either take those remaining 4 electrons, because remember we used up 16 so far, so we have 4 valence electrons left over. And we can take those and we can double bond the oxygen to the carbon or double bond the oxygen to the hydrogen. But remember, the carbons and the hydrogens are already happy. They already have their octets or their duets, so they don't want anything else. So what we can do is we can go ahead and put lone pair electrons on oxygen like that. And then if we count around, we can see that oxygen has 2, 4, 6, 8, and it's satisfied the octet rule there. And if we want to check to make sure we used up 20 valence electrons, again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Ding, 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 ding. Okay, so just to draw that structure for you guys again, without all of the garbage in the way, there it is right there. And we saw this molecule before. This is ethanol. This is C2H6O. And ethanol has an isomer. So those of you who are sitting at home going, wait a minute, what if we stuck oxygen in between those 2 carbons? Yes, you can do that too. So again, we're going to have 20 valence electrons available for this structure, because adding up all the valence electrons for each atom is going to be exactly the same as it is for ethanol. And we can go ahead and go, okay, let's put oxygen in the center like that. And let's go ahead and be symmetrical about this and put the hydrogens around the edge. And then here we can see that we've used up 2, 4, 6, 8, 10, 12, 14, 16 valence electrons, and that means that we have 4 left over. Now, each of my hydrogens has a duet and it's happy, so we don't need any lone pair electrons on hydrogens, and hydrogens don't want lone pairs anyways. And each of the carbons has an octet, 2, 4, 6, 8, and 2, 4, 6, 8. But the oxygen only has a quartet. And good thing we have 4 electrons left over, because we can give it 2 lone pairs. And that structure right there is dimethyl ether. So to draw it again for you guys, this is dimethyl ether. Now, what would have happened if you would have put some bonds in other places? Well, let's take a look at that. So what would happen if we had this structure and we had 4 valence electrons left over, and instead of lone pairs, we went ahead and we double bonded the oxygens to carbons? Well, we would have used up 20 valence electrons, which is one of the criteria that we have to satisfy for a correct Lewis structure. But the second criteria that we have to satisfy is that all of our atoms have to have their octet or their duet. And if you look at carbon, you've got 2, 4, 6, 8, 10 valence electrons around carbon, and that's not going to work. So again, if you draw the wrong structure, you're either going to have an octet problem or you're going to have an electron number problem. And that's going to tell you you're going to need to redraw it until you satisfy both of those rules. All right, so the next time I meet with you guys for the next video, we're going to talk about a few little shortcuts that will help you draw structures a lot quicker. All right, till next time, bye-bye.